My name is Amanda Graham. I am the academic director at the Irving Institute for Energy and Society here at Dartmouth College. And it's my great pleasure to welcome you to today's iteration of our New Energy series. As many of you may know, the New Energy series was launched 2 years ago to ensure that there was a good platform for young scholars in the energy and society space to share their work broadly. And we've actually just been thrilled with the level of participation that we've had from numerous universities, from scholars. We do this every 2 weeks throughout the academic year, and so it's really a great way for us to start to see the emerging work, right, of our newest members, right, of the Energy and Society Scholarship field. And so today is a landmark for us. It's the very first time that we have had a previous New Energy speaker return as a host. So Dr. Erin Mayfield spoke about 18 months ago about her research while she was a postdoc at Princeton in their really important net zero study. And she is now a professor at Dartmouth College, and we are thrilled and delighted to have her with us. She's our Hodgson Family Assistant Professor of Engineering. Her work is in sustainable systems research, and she is a multidisciplinarian, multi-method researcher. And so she is here today to host Dr. Maarten Brinkerink. And Martin, I'm going to let Erin introduce Martin, but I just want to say very briefly that Martin recently won a Early Career Researcher of the Year award at his home institution, which is the Marai Science Foundation of Ireland Research Centre on Energy, Climate and Marine Resources. So kudos and congratulations to Martin. We're really delighted to have you here joining the New Energy family. So with that, I'll hand things over to Erin for a great talk today.
Thanks, Amanda. So it's my pleasure to introduce Dr. Martin Rickerink. Martin is a postdoctoral researcher at the SFI Research Center for Energy, Climate and Marine Research and Innovation at University College Cork. He is also a visiting researcher at the Thayer School of Engineering at Dartmouth College. Martin holds a bachelor's degree in environmental science from Saxon University of Applied Sciences, obtained his master's in energy and environmental sciences from the University of Groningen and KTH Royal Institute of Technology, and has a PhD in energy engineering from University College Cork. Martin's research interests lie in energy and power systems modeling, energy markets, and renewables integration. And with that, I'll hand it over to Martin. And for the duration, if people have questions, please add them to the Q&A box. Thank you.
Yeah, thanks so much for the introduction. I'll share my screen. Which I hope is visible right now. So I'm going to talk about a methodology that I've developed over the last year that allows you to assess global climate change mitigation scenarios from the electricity system perspective. So as mentioned, I am part of Marai. Marai is a research institute in Ireland that covers a wide range of universities. And my own university is University College Cork, all the way in the south of Ireland. We have a wide range of different research areas and research focuses, among others, marine and renewable energy technologies, more the design and operation of those systems. But my own research group is energy policy and modeling group, where we mostly use energy system models and transportation models and other kind of simulation models to look at a wider range of energy and environmental policy and research questions. So my own specific focus is on power system modeling and energy system modeling. And over the last few years, during my PhD, I've developed a global power system model that we call Plexus World. This is a electricity system model that covers most countries globally, with larger countries being separated in individual regions, either based on geographical boundaries or based on current setup of electricity systems and markets. So what this model does, it tries to optimize the demand and supply of electricity based on what we call least cost optimization. So it tries to minimize the overall cost of the electricity system And it can do this either for existing power markets, but it can also do it for different kind of power systems into the future based on different projections. So depending on the research question, this model allows you to either simulate power plants, storage facilities, transmission lines, and other technologies as well at an individual unit level, but it can also do it based on a more aggregated way to reduce overall complexity of your model simulations. Right now, based on the reference model, it includes more than 30,000 different individual power plants and storage facilities. So the model allows you to simulate markets individually, but it also allows you to optimize the investment and operation of transmission infrastructure between countries and regions as well, which opens up a wider range of research questions. So this model is fully built based on open data sets. For example, the World Resources Institute released a global power plant database, which has detailed data on most power plants globally. It covers about 85% of power plants worldwide. We also use the Global Dam Watch database, which has very detailed data about hydro dams and hydro reservoirs globally. And also from the Department of Energy here in the States, a very detailed database on existing storage facilities globally. So just an example here, this is an animation of some of the output of the Plexus World model, in this case for a week in February in 2015. And what it shows is basically the hourly operation of power plants. In this case, you can see a clear dominance of coal power plants in Central Asia, India, and parts of China as well. So we can use this to look at the current day system, but we can also use it as a basis to identify specific research needs in countries globally. So what you see here is an overview of in this case, the first week of July in 2015, that shows you the emission intensity in terms of kilogram of CO2 per megawatt hour of generated electricity. What you can clearly see here are some of the hotspots when it comes to emission intense electricity generation around the world, especially in India, parts of China, especially more around the coast where the demand centers are, and Australia and Japan as well. So this is the existing model that I built. So, but for this specific research, what we've done is create a methodology that allows you to link this model with so-called integrated assessment models, which are different kind of modeling tools. So some of the differences between both model types, Plexus World or power system models, global power system models in general, are mostly used for what we call more snapshot analysis of a given power system for example, a given year. Because of it has a very limited sectoral representation, meaning that it purely focuses on the electricity system, but doesn't take into account any necessary relationships with other sectors, for example, the transportation sector or the heating sector, etc. But because of its narrow focus, it has a very strong spatial and what we call temporal modeling resolution. Temporal modeling resolution says something about the detail of variability that you can include in your simulations. For example, when it comes to the detail which you can simulate the operation of wind and solar technologies and its variability throughout time. So here on the left, you see a map or the spatial resolution of the Plexus World model. Again, every country individually and larger countries separated in multiple regions. And then when we talk about integrated assessment models, these are models that are generally used for assessing long-term pathways for the development of the overall energy system and its impact on emissions. It has a very broad sectoral representation. So these models generally do not only optimize the energy system, but they also take into account effects on land use, effects on water management, effects on the wider economic system, but also on the wider climate system. But because of this broader sectoral representation, it means that it generally has very significant limitations in the spatial and temporal modeling resolution. So here on the right, you see an overview of the spatial resolution of the message globium model. This is one of the more commonly used global integrated assessment models, among others, for the IPCC climate reports as well. But the main point here is that because of these very different setups of both models, they are complementary, and there is potential to link them up to make use of the strengths and mitigate some of the weaknesses of both model types. So why would we do this? Again, because of the changing energy landscape, and there is an overall question on how reliable these integrated assessment models are to simulate the functionality of these potentially new ways of operating power systems. So why furthermore? Because we're able with this framework to assess existing integrated assessment models and their scenarios with higher modeling resolution. We can help with assessing a wider range of input and output parameters of the integrated assessment models. For example, when it comes to assumed generation values, the use of storage and transmission, but also from a more reliability perspective when it comes to factors such as unserved energy, which is the share of demands that cannot be met, but also curtailment, which more indicates the share of wind and solar that cannot be used because of a mismatch between the demand and supply at any given time. The linking within this framework can be done bidirectionally, meaning that we're able to assist with optimizing the way the power system is represented in integrated assessment models. So why not, or why hasn't this done before? Historically, it has been shown that repeating a soft link exercise can be very complicated and time intensive because of the different data structures of models and because of different ways models are set up and are being run. And also because power system models were mostly restricted to continents as large as spatial modeling scope, because existing power systems are mostly restricted to state level or country level, or in some cases, like in Europe, between multiple countries. So what has changed? Because of this framework that we've developed, it allows for a more standardized and automated way of soft linking global integrated assessment models with global power system models. And also because multiple newer global power system models have been developed in the last few years. So this is Plexus World, but also a range of other models. So a quick overview of the framework. It starts with a general simulation of an integrated assessment model, after which a few steps are required to downscale some of the outputs from the integrated assessment model to a level that can be used by the power system model. And this is both relevant at the spatial scale, but also at the temporal scale. Again, to go from the limited amount of regions in the integrated assessment model to a more detailed amount of regions, as well as from a time perspective. The fourth step in this framework is what I call a power system model capacity allocation step. And I'll describe this in more detail after this. And it finishes with a general optimization in the power system model, where you match demand and supply either based on least cost or based on least emissions, or a combination of different objectives. And as I said, this framework is iterative, so it allows you to perform recurrent simulations to assist with optimizing the integrated assessment models. Yeah, so an indication here of the differences between modeling resolutions. So on the top left, you see the larger China region within the integrated assessment model message globium. And in the lower left corner, you see the same spatial area, but separated by 40 or so different regions in the power system model, where China is separated in about 30 different regions and other countries individually. Now, from a time perspective, integrated assessment models, again, are used for more long-term planning exercises, where time steps in the simulations are often on a yearly basis or on a 5-yearly basis, whereas the power system model in this framework is used to assess the outputs from the integrated assessment model for a specific year, but with higher temporal resolution. Now, some insights on the required downscaling that we apply. In this case, regarding electricity demand as one of the outputs from the integrated assessment model that the power system model uses. For a proof of concept application, what we've done is apply a linear regression. So based on historical values for electricity demand versus GDP and urbanization shares. So just as an example here on the right, on the x-axis you see GDP, and on the y-axis electricity demand per capita. And every red dot here represents a historical value for a country within, in this case, the larger Latin America region of the message globian model. Then we have projections for the independent variables, in this case for GDP and urbanization share, and this can be used to project your demand into the future. So that's what we've done here to downscale from the larger regional level in the integrated assessment model to country level for the power system model. Now, besides the spatial downscaling of demand, it also needs to be downscaled temporally because in this case, the power system model operates based on hourly time steps. And for this proof of concept, again, we've just used historical time series for electricity demand. In this case here on the right for Brazil, where you see the blue line being the reference demand and the orange line being a projected electricity demand time series at an hourly value. So we've just linearly scaled the historical time series based on the difference between historical demand and projected demand. And further downscaling then can be applied to a sub-country level, in this case, for different regions within Brazil. And this is being done for all regions in the global model. Now, regarding spatial downscaling, what we call the capacity allocation, as I've mentioned before, what we basically do is we use the outputs from the integrated assessment model, in this case for power plant capacities, which you can see here on the left for the FSU, or former Soviet Union region, in the message globian model. We use this as a constraint in the power system model and allow the power system model to optimize the allocation of different generator technologies to the different countries and regions. So that's what you can see here on the right. And it's important to realize that the sum here on the right of all capacities is exactly equal compared to the bar on the left, meaning that the assumed power plant capacities in a power system model are always equal to the outputs from the integrated assessment model, just with a more detailed spatial resolution. And this is done based on optimization. Now, this optimization occurs, takes into account multiple variables, for example, costs, but also resource potentials in different countries and regions globally, and also the efficiency of different resources. So you can see that here, where you see a lot of solar in Southern Europe, a lot of hydro in the more Russia area, a lot of wind on the outer edges of China because of the higher efficiency there, and more nuclear baseload and solar in the demand centers in China. Now, some example results based on this exercise that we've done initially by linking message globian with Plexus World. One of the main observations that we've seen based on some of these simulations is that the overall generation of wind and solar, given the same amount of capacity in the Plexus World model, is significantly lower compared to what message globian reports. There are multiple reasons for this, and one of them I'll explain in more detail after this. But at the same time, what the results also showed was that the amount of curtailment, so again, the amount of electricity from wind and solar that cannot be used at a specific time because of a mismatch between when the wind and solar technologies are available and when the demand is occurring. It shows that this is underestimated in message globian as well, compared to the more detailed operations of our system. So overall, what we can conclude based on this is that there is a mismatch between the demand and supply. At sometimes there is oversupply, and at other times there's undersupply in the system. And one of the main reasons why this pops up in the power system model simulations is the fact that if electricity resources are to be shared between regions in the power system model, it means that the model needs to invest in transmission infrastructure, but that it also needs to operate the transmission lines, including transmission losses and transmission costs as well. Whereas if you look at the way trade is being modeled in integrated assessment models, it is generally assumed that there are no constraints of trade of electricity within the larger regions. Like I said before, Message Globium has 11 regions. For example, Latin America is one region. So any assumed trade of electricity within that region is unconstrained. And this is one of the key reasons why these differences in the potential for wind and solar occur between both sets of models. Now, to quickly summarize the framework, it is designed again to assess scenarios from integrated assessment model with higher resolution from power system perspective. And we've shown this by a successful proof of concept by linking Message and Plexus World. Some of the strengths of the framework are the fact that we're able to automate the overall workflow, but also automate the data formats that are being used. In this case, the so-called IMC data format, which is a data format that most of the global integrated assessment models use, so that it allows for model comparisons and result comparisons as well. And by doing this, we not only allow the framework to be used for looking at results from different integrated assessment models, but it also allows for using a different kind of power system model to do the same. So we haven't just focused this on a model that we use. And because this allows for iterations, it really is helpful to support the integrated assessment modeling community by regularly benchmarking their results and regularly re-improving the way they represent power system dynamics in their models, which historically has been one of the main criticisms for the IAM community in general. Now, some of the limitations, again, as I've mentioned, because of the very detailed modeling resolution in the power system model, it can get computationally quite intensive, which basically means that as of now, we're not really able to perform longer term planning exercises with the global model at this very detailed resolution. And a second important factor is that because of the very different sectoral scope between models, it often makes integration of both model types quite complicated. For example, you have certain technologies like production of hydrogen from electricity that is not just relevant from an electricity system viewpoint, but this hydrogen is often also used in transportation or aviation or other sectors. And this is not something that is very easy to integrate in a purely dedicated power system model. Now, some ongoing work on this end. So we moved on from this previously applied proof of concept to a wider range collaboration with all 9 global integrated assessment modeling teams that are involved in providing the scenarios for the IPCC Working Group 3 climate reports, the last one which has just been released. And what we're doing is basically take a sample of these scenarios and provide additional insights from a power system viewpoint in the ways different kinds of projected net zero global energy systems might operate from a power system perspective. So why is this relevant? So this chart here on the left shows basically the relative share of electricity in overall final energy demand. And right now, current days, this is between 15 and 20%, depending on where you are in the world. But this can increase to between 40 and 70% in the future, which means that there will be a significantly larger role for technologies like wind and solar, but also technologies that help with mitigating some of this uncertainty and variability that wind and solar brings into the operation of power systems. So this is why we perform this for a sample of scenarios. And also because these integrated assessment models clearly show that there is a wide bandwidth of the expected share of wind and solar in this case. So VRS stands for variable renewables. So this is the relative share of generated electricity from wind and solar, which is expected to increase significantly as well. And with this, I like to finish. Yeah, that's it. Almost, sorry, last slide. So some of the key outputs based on this as well then. These global integrated assessment models are very relevant for energy and climate policy on a global scale, and because of that have historically been prone to criticism from other research areas. But with this framework, we're able to assist the community from a more electricity system viewpoint. And because of that, we also contribute indirectly to energy and climate policy in a global space. So from a more innovation viewpoint, the model we've developed, the Plexus World model, is the first of its kind, and really helps us to extend the boundaries in the field of power system modeling, and opens up a wide range of new research possibilities, like the connecting to integrated assessment models being one of them. Then from an engagement viewpoint, the last few years, this framework and this work has helped us to create a more formalized bridge between the integrated assessment modeling community and power system modelers outside that. And all the data sets and the input data, but also the output data from these exercises has helped us to contribute to external capacity building efforts as well. So both the Plexus World model as well as the data sets are already used by a wider range of institutions that focus on capacity building exercises in the developing world. And that is it for me. Actually is right now. Thanks.
Great, thanks, Martin. And if anyone has questions, please add them to the Q&A box. I'll start out with a few questions. So if I'm interpreting this correctly, in part, you're validating the integrated assessment models using your power systems models. In part, you can call it validation. How are you validating your power systems models?
Yeah, that is a fair point. So there are 2 points on that. So the first one is that the power system model is validated and benchmarked based on the current day, so current day generation values and current day emissions. So what we've done is have our baseline model and calibrate that with historical reported data from, for example, the IEA when it comes to generation values in different countries on that end. So it is calibrated and validated on based on 2015 and 2020 as data years. For future simulations, there's always more uncertainty, again, because you're also are dependent on input data and projections far ahead into the future, which is always uncertain. So that is harder to calibrate.
So when you're working with integrated assessment teams, are they endogenizing some of what you're producing into their models, or is this more kind of a second stage validation and not kind of the bidirectional kind of flow?
Yeah, so this is something that we've done with Message Globium as one of the integrated assessment models, where we've used the outputs from Plexus World when it comes to electricity trade mostly, because that has been identified as one of the core underlying issues. We've used some of those outputs as a renewed input for Message Globium. And this is also something that we want to, so besides the study that we're working on right now, so where we mostly benchmark existing scenarios, that would be the next step after that, where we, for some of the key input parameters, try to do that in a more iterative way.
So, as you know, I'm interested in the spatial downscaling beyond country level. Do you see that potential room for a framework that integrates kind of your planning scale, your power system scale that you work on, to the integrated assessment scale? Do you think there's value in that, or how could you see that working?
So I think from a theoretical viewpoint, I do think there is value in that, especially because when it comes to more planning side of things, especially at a local scale, this is something that is not even really taken into account in our power system model, let alone into integrated assessment models. So I do think there's a very theoretical benefit to that. The main issue there is that it's very, very difficult to get globally covered data sets at that scale, because that's something that we've already seen in trying to downscale from a country level to, let's say, the larger regions within the US and China. There are not really these wider covering data sets available that help you to project, for example, demand into the future at a local scale, but also renewable resource potentials at those scales outside the more data sets that, let's say, the EIA supplies in the US, but for other regions in the world, that becomes a lot more difficult. So that's more a practical limitation.
Yeah, and oftentimes where many of the decisions are being made with respect to mitigation are at your local, in the US state level, right? Those where things are, mitigation is happening. So being able to translate those smaller scale decisions to how this actually rolls up, not just to country targets, but how this kind of rolls up into kind of a global perspective. I feel like that conversation happens oftentimes at the local scale. Well, does this mean anything? Or are we actually going to meet a net zero target? And what does that even mean for a state meeting a net zero target in terms of the broader picture of climate change?
Yeah.
So we have a question from, I believe, a student asking about courses that you recommend taking for those interested in climate and sustainability. They seem to be interested more on courses related to greenhouse gas counting and verification and those sorts of courses. Do you have any general recommendations?
Well, I guess that you're really dependent on where you are, I guess. But for me, I've reached this point from a bit of a different angle, right? Where my focus was more on environmental science, and I got into modeling later on, mostly by learning by doing during my master's and PhD, I guess. But I think that generally any introductory course to climate modeling, energy system modeling, environmental modeling, more on the concepts, not so much on how one specific model works, but more on the differences between optimization and simulation, that sort of things. I think that is very important to have as a basis before really diving into the details of different tool sets.
Great, thanks. So I guess for those who are less familiar with integrated assessment models, can you speak more towards the types of information that integrated assessment models provide that power systems models don't provide, which is why you're making this linkage?
Yeah, so again, like I said, integrated assessment models are more used for long-term planning exercises, but not necessarily solely focused on the energy system, but in correlation with impacts on land use and other environmental and climatic and economic impacts as well. So they provide a much wider set of results and outputs that we can provide with a power system model. But because of that, the outputs from solely an electricity system viewpoint, but also the inputs are fairly limited. For example, when it comes to let's say, generation values or assumed generation values, because again, these models operate based on yearly time steps. So generally it works that they assume that wind can contribute X amount of terawatt hours per year, whereas we have much more detailed representation of wind and solar. So for us, it actually is not so much an assumption on how much it can contribute. It's more a output based on optimization. So there are very different approaches on that end. Plus that we're also able to just provide a much wider range of outputs on costs of generation, reliability factors from a power system viewpoint. Yeah, and more in that direction as well. So it's a different scope on what you're trying to show, I guess.
Mm-hmm. And so where do other types of macro energy systems models fit in, especially thinking about your energy system pathway models that are not just the power system, consider other sectors, have a good representation of the power system itself? Kind of where do they fit into this whole picture?
Yeah, and that's a good question as well, and that's also something that I've run into over the last few years, especially because what I've realized is that there's a benefit of trying to improve your modeling resolution from your detail in time and space as much as possible, but there's a trade-off on how how many simulations you can do, but also for how many years into the future you can do it. And because of that, one of the other things that I'm working on right now as well is to create a energy system model that is more focused on the expansion side of things. So again, trying to project the development of your energy system into the future. So that is more a model that lies in between these two. And we're also working on trying to integrate that model as well in this entire framework. So there is space for that as well, because the power system model does not always take into account the right interrelationships with other sectors in the wider energy system. So it's a very, very relevant question. And yeah.
So we have a question from a student, John DeFaris. He's asking if you have done any back testing and what kind of back testing to validate the predictive power of the frameworks and models. And if you've done some of this work, are there any interesting discrepancies that you have found?
I'm not sure what you mean exactly with predictive. Can't see.
Maybe that's kind of a first question. Are your models used for prediction, or?
Well, they're models used for prediction on the side of the integrated assessment model regarding, in some cases, the predicted impact of certain technological developments on GDP, for example, which then affects your expected increase in demand. So on that side, there is, but on the side of the linkage between integrated assessment models and the power system model, not so much on that end.
Yeah, I mean, how I often see these, they're scenarios. None of this is predictions. It's based on different actions that we choose, right? And so these are just the broadest contours of different sets of actions that we can choose.
Yeah, and also because the power system model, at least, is a static model. So whatever comes out is based on your own inputs. So it's not that if you rerun the model multiple times with the same inputs that you will get different probabilities for outcomes or anything like that.
Yeah, and I'll also mention on the question of kind of model validation, there's some work that looks at empirical accuracy kind of at the country level. So Evelina Truvanite's group has done some of that work. I'm not sure if you've done any of that in your research. There's not much research in that area, I would say, actually. Okay, so I kind of moving on to questions of how this translates into this informing decision making. And so you noted that you were working in collaboration with teams that were contributing to the IPCC. Can you speak more about how you've used these tools to help inform decision making, or how these tools could be used to inform decision making at different levels?
Yeah, so it's a bit early stage for that still, because we just finished with this proof of concept exercise and are now working on the first phase of actually trying to look at results that have policy merit. So on that end, it's a bit early stage. But what we are doing is already helping with some of these models by means of bilateral discussions to assist with improvements in their in the model infrastructure, which then in turn in new studies will have impact there directly. And I think a second, at this point, probably the bigger factor is the fact that especially the data sets, well, the model data set, in a broader sense, the Plexus World model data set, is helping a wider range of groups to improve the data side of things in their own models, which then in turn are being used for capacity building efforts globally. So, and then again, so it trickles down, right? So then if those teams use the model with renewed and improved data inputs, that will have impact from that direction as well.
Mm-hmm. So you are kind of a developer and seeing that you can help educate those to actually use these models in decision-making contexts, kind of on the ground. Is that how you see your role, kind of?
Yeah, or at least assist with identifying and improving some of the low-hanging fruits in these models. Yeah.
Mm-hmm. Okay. So again, if people have questions, please feel free to add them to the Q&A. So I guess I'll kind of open it up to Martin if you want to talk about any other kind of upcoming research that you're working on, or other directions that you would like to see this work go in the future, or what you think is needed by the field more broadly.
Yeah, so on this particular piece of work, I think the next important steps are both going to be to not just, assess existing scenarios, but also perform more structured ways of improving data inputs and data structures of the integrated assessment models that we work with. So that's an important next step, I think. And that is hopefully something that we'll start working on after this cycle of studies. So that's one side of things. And the other part that I'm excited about is the more outside this framework, in general, the work that we can do with this these newer global modeling tools that allow you to both look at more macro questions, but also allow you to zoom into research questions in specific areas in the world that to date might have been overlooked, I guess, or overlooked, not paid too much attention to, compared to the general modeling studies that we do for Europe and North America and that direction. So I'm just excited about the fact that this work and the data enables a wider range of research in the future, for sure, and not just for me, but also for others. And I think that is the part that makes me excited about doing this stuff. Anyway.
Maybe do you want to provide some examples, especially for students on the call, of the different types of questions at different spatial scales that you can answer using these modeling tools that you are developing?
Yeah, so starting at a global scale, I guess one of the concepts that has been proposed over the last 10 plus years is the idea of a global electricity system that is completely integrated by means of longer distance transmission infrastructure and by means of sharing resources between continents. So that is something that has been proposed numerous times and discussed, but it's not really quantified very well until now. So that is something that we plan to start working on in more detail, because this is the kind of tool that that allows you to do that. I guess on a country level or a region level, but at larger spatial size still. A tool like this also allows you to, by solely focusing on a specific region and not doing a full global simulation, it allows you to assess a wider range of different pathways for decarbonization of your overall electricity system. And you can do this either individually, or you can assess whether it's more efficient to integrate a neighboring power system into your own. For example, what is happening in the northern US with parts of Canada as well. So these are the kind of studies that you can do with that. And the flexibility of a model like this allows you to focus on these different research questions at different spatial size.
So in some of the modeling frameworks that you work with, can you answer questions at kind of quicker time scales, in the sense that of, for example, in the situation in kind of Ukraine and the changing European energy system, to both kind of short-term decisions and the medium-term decisions with different changing resources of natural gas and transmission?
Yeah, exactly. So that is something that actually a different research group in Europe has done that, where they've extended their European power system model to also include more Ukrainian power system, but also fuel supply constraints based on different scenarios. And they've compared that to the existing setup. So it's both on a spatial size and on a temporal, on a time, the detail and time that you include in a model like that. It allows you to compare these different kind of setups and what it would mean directly from a policy viewpoint as well. For example, where Europe right now is proposing to go off Russian gas and oil in the near term. This is something that you can very quickly integrate as a scenario in these models and run it through to see what the impacts are on a cost perspective, but also emissions, and also on the reliability of energy supply, for example. And that is also no doubt what is being done right now within the European Commission and other institutions that are aligned to walk this through, to run this through.
Yeah, and it is, I would say, from my own experience, it's hard to spin up a model to be very responsive in kind of the near term to quickly changing politics. And I know that's something we've been trying to do in the US context, and spinning up a model, even if you had a kind of a robust model of the European system, spinning up a model in time to be kind of responsive can be kind of difficult. And I think it was interesting because the time it took for kind of one group that I know to spin up a model, they were already actually changing the physical infrastructure, and there was new physical integration. So that's just to say that these modeling tools are very powerful. There's a lot of room for improvement to help with immediate term decision making as well.
Yeah, I think it's important to again stress that these are numerical models that are fully dependent on your data inputs, and especially on the data input side of things, they're often the biggest limitations. So there's no whatever answer comes out of these models, it's never guaranteed or 100% accurate. Absolutely not.
So when you're using these models in different contexts and speaking with non-modelers, how do you typically try to communicate model outputs, or what types of modeling outputs are the most useful? I know you were showing different visualizations, and kind of how do you communicate these insights?
Yeah, so if I if I would be speaking for a non-technical or academic audience, the only thing I'd really include would be some of these visualizations, because it's for me, it's over the years I felt that it's a lot easier to explain certain dynamics, or if people have an understanding, or if they can actually see what's happening. And I think that is, for me at least, has been a key way of communicating with these type of audiences, I think.
Yeah, I think some of the higher level kind of messages that are most powerful in especially in the mapping types of mapping visualization is just how expansive the infrastructure actually changes actually are in these net zero futures. I mean, we're talking about completely changing our systems, and I think most people don't truly or viscerally recognize how different our infrastructure systems will be and how it will affect kind of every community as well. I don't know if you've experienced similar.
Yeah, I think it's even the graphs I showed at the end. Still pull it up. Graphs like these are very powerful as well, where you just show how insanely big the potential change in the system overall would be compared to current days. And I think that is a very, very clear message by showing it like this.
I guess we're close to the end of time. So if there's any kind of final words, Martin, that you kind of want to share and concluding thoughts.
So nothing in particular that I haven't said before, but I think it is important to recap a bit on what I've said before, is that especially the integrated assessment modeling community has gotten quite a bit of criticism over the years, and whether you think that's whether that's fair or not. I just think that it's important in general with any kind of field to be open towards improvements from other angles, and I think that that has been very positive over the last year or so, last years. So that's one of the main things, and the other thing is just that I'm excited about this this kind of work and what it opens up into the future as well on other kind of research questions that we can approach. So those are the two main messages, I think, for me at the end.
Great, thanks, Martin. And so those who are physically in Hanover or at Dartmouth, I just want to point out that Martin is physically visiting, and he has an office in the Irving Institute. So please do reach out to Martin, and I'm sure he'd be happy to talk about these power systems models and how you can get involved in working on these types of projects, because there's a lot of important questions in this space and room to get involved. And Martin, I don't know if you have a slide with your contact information for. Or you can...
No, I do not, but I have this one. I mean, if you go to any of these papers, my contact details are in there as well.
Okay. Great, thank you. So I guess with that, we can end there, and thank you everyone for attending.